do another round of hardware stuffs. Now that you have FSM that can identify when bytes are correctly received, add a data path that output the correctly received byte. Out byte needs to be valid when done is 1 and don't care otherwise. So this is 4B because why? This is 1, 0, 0, which I guess is 4. And then 1, 0, 1, 1 is B, because 1, 1, 0, 0 is C, so minus 1. So just do that for my FSM, and then my out byte is just going to if my state is data, then if my state is data and counts not 8, yeah, then just shift in the data, okay? If state is data and count is not 8, then so this is LSB and this is MSB. So MSB shifted in last. So on this one, we don't shift in anything. But for 0 to 7, we're going to have in as MSB. And then I will discard the LSB. So that means 7 to 1. So this would go into 7 and then okay. And otherwise, I guess just clear it. Out byte is not declared. Oh, out byte. So the next problem also depends on this problem. Oh no, okay, this one is this one. So the error was missing this because I can only clear it after we release it. So if data equals, if we're in data and count is 8, i.e. this cycle, we still have to hold it for one more cycle. In this case, I just say hold it for one more cycle. And then, yeah, whereas before I would clear it beforehand. So I would clear it at 8. But if I clear it here, then I can't flop it out in the next cycle in my out byte. So anyway, yeah, this one is needed for the next question. So do this. And then there's some parity checking thing. Change your FSM to perform odd parity checking and start done signal only if a byte is received correctly and its parity check passes. Yeah, this is another spec thing that's very confusing. So here it says, identify start bit. Okay, wait for all 9s, and now an extra cycle where this parity bit must, I guess, match the input. We'll use odd parity where the number of ones in the 9 bits received must be odd. For example, this satisfies the odd parity we want to add parity checking. Parity checking adds 1 extra bit after each data byte. So this or this, who knows. We will use odd parity where the number of ones in the 9 bits received must be odd. So this is 5 bits and this doesn't have 5 bits. Okay. So I take this, and then each cycle I would, in the data, I would use this to see if it's odd or not. And so I find a stop bit here, and I output the data without the parity bit here. Okay, so high level, our count is 9 instead of 8 now. So this would be 8 and this is 9. I would just say, if not 8 or 9, then we would latch the data. So basically 8 is 1 0 0 0 if I'm not mistaken, 1 2 4 8. So then basically if MSB is asserted, I stop shifting in data. Otherwise I keep the data. So I hold the data here and here, and then I release the data So 0 to 7, I shift in the data. If it's 8 or 9, I hold it. So 8 and 9, I hold it. And then otherwise, it's 0. And then the count here is basically saying if it is 9, then the next count is 0. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0. But if it's like this, I can actually just do this because there's no 10. So we just go back to 0 here, and then we release the data like this. So that handles the case where so it's 9 and 9 basically. So if it's count equals 9, and so here and input, then we go back to this wait 0 state where we wait for the next data. If it's count equals 9 and not in, so if this was 0, we go ahead and do go back to the error, but we'll come back to that later. And then right now what we've done is we've handled this extension of one cycle where we can now accommodate for the parity bit. So when count equals 9, we have the parity bit. So here 4B is 1, 2, 3, 4, 5. And then this is the stop bit. So 5 is odd, so then that's good. So then we give a done. Only if a byte is correctly received and its parity check passes. So here we have 1, 2, 3, and 4. So we don't have it. We have a stop bit here, and then we discard everything, I guess. Start 0. The part that's that's fine, because for this we can just instantiate parity, reset, and clock, and basically if I have my stop bit, I just need to check if my parity is odd. And then I can always just reset it here. I guess you're always in reset if you're not in. I can reset it here once I'm out of the data phase. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it's all reset for this parity. And if data it's basically parity and I can say reset if this, so don't reset if here, and if I'm in state data, then my input counts, and at this cycle, namely count equals 9, I'll take the parity and make sure it's odd before I output anything. So where's my data done? I mean, so this means that let me expand this out. So count is 9 and in is true, and odd, keep in mind odd has the parity check for here all the way up to here. It will also check here, I'll put it next cycle, but we don't care. So if it's odd here and we have a stop bit, we're Gucci. So we output the data here in this specific case. I think you still discard the next byte. Okay, so there's two cases to consider which we fail parity. If we fail parity, then this is 0. At the time this stop bit is set, which is this guy. If this is 0, then we won't have done next cycle, so that's cool. And suppose we don't have a stop bit, same thing, we don't have a done next cycle. And then we discard everything, and if count equals 9, then regardless, we're going to be in the wait 0 state. Well, if count is 9, we're going to go to the wait 0 state the next cycle and then start receiving data. But then suppose this stop bit was 0, then we actually go into error state, and then we have to wait for the stop bit to go up again to go to this wait 0 state, and then wait 0, then if it goes away, we can go wait 0 state, and then it'll go wait 0 state, and then the data phase, which is like again another 10 cycles, so 0 to 9. Can't declare implicit thing odd. Okay. Okay, forgot to declare it. Cool. And then what about this next one? The sender inserts a 0 after every 5 consecutive ones, which receiver must detect and discard. What about cases where you have 0, 1, 0, 1, 0, 1, 0? I guess we don't. So this is plus 2, 7 bits. As soon as, so this will be all ones in your byte stream, and then this will be 0, meaning it'll be 1 1 1 1 1 1 1 1 0, and if it's 1 1 1 0, it actually deasserts it the next cycle. So we're just looking for this, or if this, all ones. I guess, yeah, I guess no outputs given if, you know, like here. Like if this is 1 0, then there's no output. And reduction says all 1. I did an OR reduction, which was incorrect. Okay, and then this kind of sidesteps the fact that you would normally have to write a very annoyingly large state machine. Okay, so I'll close these now. I know it says to do FSM, but no thanks. I've done enough of that to not want to do that. Next stream. It's just going to be stream of 2 to 1, and then 1 to 0, and I pop out the MSB, and then I would put next stream in. Sorry, I would put X in, and output Z is when next stream is, I believe that's a milli. Current state and inputs. So I guess mealy and more, the difference is like using stream equals 101 versus next stream, or no? Okay, so my understanding is correct. So MSB is newer in time, so then we would shift, right shift anything. The machine will accept input numbers of arbitrary length. The circuit requires a synchronous reset. Conversion begins when reset is released and stops when reset is asserted. Asynchronous reset. So here it is 110, and what is 110's 2's complement? Right? So 0, 1, 1 plus 1. So I guess I don't get why. I guess I don't get what the output's supposed to be. Oh, this is 100, which means 2's complement is going to be, yeah, 100. So series of bits beginning with the significant, and the output Z is the 2's complement of the input. One zero zero. 2's complement of 100 is 100. Oh, maybe unless they mean like the next cycle, then 100 100, then that makes sense. Then what about this? This is 0 100, which is going to be +1. So we have this 1100. So it does look like we give the 2's complement in the next cycle. what are the rules of 2's complement? So pattern recognition suggests that we start at 0, and if we encounter a 1, then the next cycle will be a 1. And then if, let's say, so 0, 0, we have a 1 again. So and then this. So if I'm outputting a 1 as I'm here, here, and I encounter a 1, then I want to output a 0. So it's almost like this will XOR this, boom, and then this will XOR this, boom. And if I have a 1 on a 0, it still gives 0 for some reason. So here this would XOR this, but this doesn't give a 1. Okay, so let's 1 1 0 0. Okay, and then if I do the whole thing, so 1 1 0 1 0 0 1 1 0 1 0 0, then I want to invert it. 0 0 1 0 1 1, and then do this. So if you encounter a 1, then a 0 is XORed. Let's say state 1. If in state 1, then next so suppose we're in this state 1, 0, 0, and we go ahead and do 0, then we end up with 1. What if we did 1? Then we would have 0, 0, 1, and we'd end up 1, 0, 0. So when do we change states? If oh, this is more, so yeah, it is one cycle after. Okay, so that's up to 0, 1, 0, 0, and then so suppose 1, 0, 1, 0, 0, like this. I don't know if we're still in the same state or not, so let's just see if the rules apply. So if this was like this, then you'd end up with like 1, 1. So you'd end up with 1, 0, 0. So this is the same as this, which is just sine. Oh, it's like, so you go here and then adding 1s is just a sine extension. So adding 1 is a sine extension, so you always just output zero, right? Yeah. And if you go to 0, what does that mean? Oh, okay, so maybe instead of, so I think this part is easy, but then we can say we encounter, what rules can we say? So this is -4. And if we have a 1, we still go to -4. In which case our complement is 1, 0, 0. The same. Or, because sine extension, and input 1 means, sorry, sign extension. But that's only for the saturated value, right? So like what is this? This is 12, so this is negative 12. So this is what, 16? So 16 plus 4 is 20. Yeah, I thought I could have had some multiply by 2. This is right. Yeah. If state is 2, then so I mean this is still XOR of X, so what about this 0? Then no, this is the same behavior where we XOR it. So here, no matter what, the next output is the XOR of this one, and then here, no matter what, is the XOR of this one. Okay, and then what else? Then next is adding a 1. Which implies zero zero 1 0 1 1 this, So this is still that same XOR behavior. So now is it just that simple, like at the beginning you um, okay, 0, 0 plus 1, and then let's say 0, then 1, 0, 0. Seems like the first bit's the same, all the rest of the bits are flipped. Same here, like first bit's the same, rest of the bits are flipped. What if this? Then it's flipped. So is it true that it's just actually so if I encounter a 1, then next cycle onwards is just the flip of the thing. Like here, if you have a stream of zeros, then obviously you have zeros, and then if you encounter a 1, it seems that forevermore it's just the flip of the bit. So, okay. Asynchronous reset. So if I haven't seen a 1, then if I did see a 1, then next cycle so this next state is saw1, so saw1's here, and then so this state is no 1s, so output z is just going to be 1 cycle after x. So state is no 1s, and then next cycle is just mimics this. This state onwards forever is saw1s, and saw1 says just take this x and then flip it for your next cycle. So actually no 1s means x, not x. So I haven't seen a 1 yet. So just, yeah. I have so a 1 is inserted here. Next state is saw1s, saw1, and then so no 1s is here and x is 1, so then z is 1 next cycle, and then here forevermore it is saw1s, so it's not no 1s, and if it's saw1s it'll just go ahead and take not x and propagate it to z forevermore. So this is just the original this thing, and okay, so what's happening? In this state we haven't seen any 1s, so next state here is saw1, so state here is saw1, and z here is just gonna be this. Oh, this is simply this. So I guess immediately it's just the differences next state versus state. So there's no mismatches. And then I guess this is the same as this, obviously with the state machine. The only difference is we are faster by 1 cycle. So we can just output it. We can just bypass the input to the output. And okay, I wanted to just like really quickly finish this melee one, and the reason for that is because I'm like, if I close these windows, I don't want to re-implement it. But it looks like if I refresh this, this is all done. So, all right, yep, that's it for this one.